Hi, this is Nikos Petrellis again, and in this video we're gonna examine the analog digital converter of the STM32F4 development board. This board offers three analog digital converters with multiple channels. In order to do a very brief introduction to what operation offers the analog digital converter, let's see this figure here. We have an input analog signal, and this signal is sampled at regular, possibly time intervals. And each time this analog signal is sampled, the analog level, voltage level, is converted to its corresponding digital representation with n bits. You can see that in this way we can approximate with the digital values an analog signal, and this representation is more precise if we use a faster sampling rate and a larger number of bits, so if we choose a higher resolution for the analog digital converter. The maximum value that the analog input is expected to have is called V reference, and this value is used in order to understand which is the minimum voltage step that can be discriminated by an analog digital converter. This is defined by this equation here, where we divide the reference voltage, which is actually the maximum voltage that we expect at the input of the analog digital converter, with a power of 2 at the n bits. So for example, if we have a V reference equal to 2.56 volts and we have an 8-bit analog digital converter, then the number of combinations that can be done in the n bits of its output is 256. So the step that we can get is 2.56 divided by 256, so we get 10 millivolts resolution. You can find several sources in the internet about explanations on how the ADC works. This is not our main issue in this video. What we will try to do is to configure the analog digital converter from the STM32Cube tool in order to demonstrate its use on the STM32F4 Discovery board. So we start the Cube MX as we did in our previous projects, and we have selected the correct MCU. Actually, we do select this in this stage, so we try to find STM32 407. Here it is, 407VG is this family here, so I selected and start the project. Okay, the project has started. Now, one pin that where an input to analog digital converter can be connected is the PA0, which is shown here, the first of the port A actually. So if I click on this and I select this to be an input for the analog digital converter number 1, okay, it has been assigned to the analog digital converter, and from this point here we can get the parameter settings. Actually, the only thing that we're gonna change here is the resolution. You can see that the resolutions offered are 6 bits, 8 bits, 10 bits and 12 bits. We will reduce the default 12-bit resolution to 8 bits because it's adequate for our demonstration, and nothing else. Let me see my notes if anything else is needed. Okay, then the next thing we will do is to define, as we have usually done in our previous projects, the output of the LEDs to the outputs of port D. These are PD12 up to PD15. So I select them and assign them to GPIO output. The second one too, the third one, and the last one. So everything is now GPIO output so that the LEDs can be driven. And I think that I can proceed next to the creation of the project from the project manager. This is the default path I have used for my previous works. I can name the project ADC, for example, and I should not forget to change this option here to MDK ARM. So if I press generate code, the project will be generated. I won't do this thing now because I have already created the project, so I directly jump to the Microvision environment. But remember that if you open the project created from the CubeMX, you will probably have to select at the device startup this option here in order to create the startup files, because the CubeMX does not create it by default. But if you do select this option here, remember from a previous video, I say again, that we had double creations of the same file. A file was created twice, let me say in other words, so I had to remove one of the files. Please visit our previous video and see this step here. I will not repeat all the rest of the videos, this option here. I have done this now. So my project, if I try to build it, I don't get any errors, as you can see here. So what I will do is to connect my board, but as you see here, what I have done is that I have connected to the PA0, which is on this header, a 3-volt voltage, which is a non-zero voltage, the smallest non-zero voltage that I can get without using additional components, in order to see what will happen here. Let me show you, let me do a demonstration and then I will explain the code afterwards. So I connected to my USB port. Okay, as you will see here, all the 4 LEDs are turned on from a previous project, but I download the new code here. Any LED is turned off right now. Flash loading has been completed, and let's connect as we have learned using this option here, options for target ADC, and go to the debug here where ST-Link debugger is already selected. Okay, and from the settings I understand that it has been correctly recognized, so I just have to start a debug session. Okay, I don't insert any breakpoint, I just run the program directly. And as you can see, all the 4 LEDs are turned on. This is because, as we will see later in our code, if the input value to the ADC is large enough, the more LEDs are turned on. If I disconnect the 3 volts from this point here, you will see that since no voltage is connected to the input, of course this does not mean that 0 volts ground is connected, but okay, in our case it will be recognized as 0. So with 0 we expect, as we will see from the code, to turn off all the LEDs. So let's do this disconnection here, and okay, as you have seen, all my LEDs have been turned off. Let's see why this happened from the code. If I stop debugging and view directly what I have inserted in my main function, here is my main function, and what I have inserted is this part of code only here. Actually, I changed the infinite while loop, which was empty. I defined earlier a variable called ADC value. And within this source code, I initialized each time a new iteration starts, I initialize the analog digital converter, and from this command here, I actually get the value, the digital value at the output of the analog digital converter. With the HAL ADC poll for conversion, I actually ask the ADC to start a new conversion. If this ends without errors, I get HAL OK. And in this case, I ask from my system to return the digital output of the ADC using this call here, HAL ADC get value, to the variable called ADC val. Then I stop the conversion, and then I check the ranges of my value. How do I check my ranges? If you can see here, I have 4 if then else commands. In each one of these commands, I do a comparison of my ADC value with a mask actually, that has a single one in a position that can be either the most significant bit, number 7 here, or the next bit, number 6 here, or the next bit, number 7 here, or the next bit, number 4 here. So, if I find, for example, that bit number 4 is on, then I turn on the LED that is connected to pin number 12. If I find that the bit number 5 is 1 at the ADC output, at the 8-bit ADC output, then I turn on the GPIO pin 13. If I find that the bit number 6 of my ADC value is 1, I turn on GPIO pin 14. And lastly, if I find that the most significant bit of the ADC output, which is bit number 7, is 1, then I turn on GPIO pin 15. So, when I had connected my 3 volts to the analog digital converter input, this means that I had a large value where all the most significant bits were all 1. So in this case, all the LEDs were turned on, as you saw earlier. When I removed the connection and the input of the analog digital converter was 0, then none of the most significant bits was 1, so none of the 4 LEDs had been turned on, so all my LEDs turned off. This is the explanation you get here, but if you like, I can give you here another example of what would happen. For example, if I got from the analog digital converter output a value like this one here. So in this case, you will see that my bit number 4 is 1. This means that this LED will be turned on, number 12, but I also have the bit number 6, 1, which means that my LED connected at GPIO pin number 14 will also be turned on, regardless of what we have at the rest of the bits. If these values were here, as you see that I changed the least significant bits, no difference would be made. The specific LEDs that I mentioned earlier, these would be the ones that would have been turned on. Of course, if we had a trimmer or a potentiometer connected at the input of the ADC, and we could calibrate, we could fine-tune the input voltage to the ADC, we could find all the combinations of the LEDs available, and we would see the results from the LEDs. Thank you very much.